Okay, hello everybody. It is the 11th of May today. I know I put 1st of May in the live stream thing. I'll sort it all out after the live stream's finished. Anyway, hope everybody out there is doing well. Hello to Sam, James, G, Emily, Sabah. Hello everybody. Hope all of you are doing well, no matter where you are in the world. I suppose schools might begin at some point. There was a big talk yesterday with Boris Johnson. But there is no firm date, and there's still no firm agreement even amongst your teachers about how schools are going to work when they all come back. So until then, I suppose all we can do is just keep doing physics. The more physics you do, the less you have to think about the world kind of collapsing around us. So yeah, let's just do some physics today. And again, although this is mainly aimed at year 12 at the moment, if you're year 13, hello, welcome back. You might be wanting to do exams at some point again in the future. And all the stuff we're doing is good revision, okay? And then we're going to be going on to some more year 13 style topics like fields and circular motion and simple harmonic motion before the summer holidays. So yeah, right, today we're going to be doing some work on interference, okay? So this is very much the fact that if you've got a wave and another wave, the two of them will interfere together. So let's just begin. Don't forget, of course, that you can find all of this stuff over on my website at alevelphysicsonline.com. And basically, we're going to have a look at some answers. So hopefully this should all be good. Yeah, and I think a lot of people here talking about exams and stuff like that. I suspect if you're in year 12 at the moment, there might not be exams when you go back to school. It might just be a chance for your teachers to actually catch up with you, see what work you have been doing, maybe make sure that there's work that you can take away with you to complete over the summer ready for next year, but who knows. Okay, so first of all, state the principle of superposition of waves. Okay, so this one here, and while I'm writing out an answer, just make sure you like the video, and if you haven't already done so, subscribe to me on YouTube. And maybe have a look at some of the questions if you haven't already done that. So basically, superposition is that when two waves meet, the resultant displacement is the sum of the displacements. And the key word here is about displacement. Okay, so the two waves might meet together and they don't just kind of collide and stop, they basically move through each other. But if we were to look at the displacement of individual bits of that wave, it's basically this displacement added to this one gives that resulting displacement. Now sometimes that can be constructive, sometimes it can be destructive, and sometimes it's going to be something in the middle. Okay, we then have a standard thing to know. We've got a double slit, and again, interference is not taught about on its own. It's often part of other things like diffraction gratings or double slits. So here we have a red light, and again, you should recall that red light has a wavelength in the order of about 600 nanometers. So 600 times 10 to the minus 9, which is 6 times 10 to the minus 7. So maybe 600, 660, something like that. It's hitting this thing here. So what does the word coherent mean? Okay, so coherent basically means you've got light sources where there is a constant phase difference. Okay, so that's the main thing, what we mean by a coherent source of waves. They've got a constant phase difference. Often they have a similar amplitude, so they're kind of which means actually when they interfere, we can actually see the interference effects. State a value for the path difference between the waves from slits S1 and S2 to the screen to produce a dark fringe. Okay, so basically when you have a dark fringe, what we have is a wave that is interfering with a wave which is out of phase by 180 degrees, or it's got a path difference equal to a half wavelength. Okay, so basically what we're saying is that when you've got something where the path difference is equal to lambda over 2, that's where the ups cancel with the downs, and we get destructive interference, which is why it's going to be a dark fringe. And here the path difference, we need to give it a value in meters. Now, if lambda is equal to 6 times 10 to the minus 7, then lambda over 2 is going to be equal to 3.00 times 10 to the minus 7. Okay, so yeah. Somebody said as well about Rohan saying, does it have to be saying a constant frequency and phase difference? I suppose by saying a constant phase difference, this implies a constant frequency of wave as well. But you know, it doesn't take long to put in about a constant frequency. When I looked at the mark scheme for this paper for OCR, it basically underlined constant phase difference, and that's enough to get you the 1 mark. But if you put the same frequency, the same wavelength, and a constant, not just phase difference, a constant phase difference, that's what's going to get you the marks. Okay, calculate the separation of adjacent dark fringes on the screen near to point P and use the following data. So for this one over here, I'm going to use the equation that says lambda is equal to AX over D. And again, you might see this in terms of W and S, so lambda equals WS over D. Depending which exam board you're doing, it's all the same. So we're going to rearrange this to make the the fringe separation X the subject, and therefore we can say that X is equal to lambda D over A. We know that the wavelength of that light is 6 times 10 to the minus 7. The distance to the screen is equal to 2.50 meters. The slit separation is 1.20 times 10 to the minus 3. And all of this data has been given to 3 significant figures. So I'm going to give my final answer to 3 significant figures. And therefore that's 6, 10 to the minus 7 times 2.5 divided by, giving an answer of 1.25 times 10 to the minus 3 meters. And then the final thing I'm going to do here is I'm going to give my final answer, because although it's given as 1.25 times 10 to the minus 3 meters, does that sound sensible? Well, yes, actually it does, because this is equal to about 1.25 millimeters, which I guess if we did it to scale, it's going to look something like this. And if you remember from when you did do practical work in school and you had access to lasers and double slits, that's the kind of thing we might get where you have some light and dark fringes of that kind of spacing. Okay, so hopefully that's helping. And again, loads of people, Oscar, excellent, 1.25 times 10 to the minus 3. If you want to put your answers down, please do so. If you get it wrong, it doesn't really matter, you know, and you can always retract your statements. So that one there, interference, has started out nicely. Now, for the next set of questions, we're going to state and explain. Okay, so maybe 1 mark is your statement, the 2nd mark is for your explanation. And what I'm going to do for these is I'm just going to put the equation lambda equals AX over D. And what we're going to look at is the position of the bright fringes. So we're going to be looking at how does X change when we alter something else. So even though this question here is about kind of a wordy question, to help me in actually my appreciation of what the right answer might be, I'm going to write down the equation to do with double slits, and I'm going to be thinking about how does X change. Okay. And G just asked for the last question, would it be okay to round it to 1.3? No, do not do that. Okay, the reason is the raw data was to 3 significant figures, 6.00, we had 1.20 and 2.50. All of our raw data was to 3 significant figures, so our final answer should be to 3 significant figures as well. Okay, didn't mean to shout. Okay, so what happens if the light source is changed from a red to a yellow light? Well, you do not need to know and remember the wavelength of yellow light, but you should recall that red light has the longest wavelength. So what we're saying here is that lambda has decreased. Now, if we're keeping the slit separation the same and the distance the same, we know that the wavelength is proportional to the fringe spacing. So if the wavelength goes down, the fringe spacing goes down as well. So that means that X gets smaller. So I would say here that X gets smaller, or the fringe separation gets smaller because the wavelength is proportional to the wavelength of light is proportional to the fringe spacing. Okay, sorry for making you jump, Brandon, when I shouted before. Slit S1 is made wider than slit S2, but their centres remain the same distance apart. So what we're talking about now is that we had a slit, a double slit like this. Now one of them has got wider. Hold on. Now one of them has got, I'll do this in a different colour. Now what we've said is that basically that slit has got wider, that one has stayed the same. Okay, so we've made this one bigger, but the actual separation, which is the distance that we measure, the distance from the centre of one slit to the other, is the same. So what's going to happen? So what we might say is what's going to happen to the position. So here, the position is the same. So we don't need to comment on how bright it is, if it's darker or brighter. We're going to say the position of the fringes is the same. And this is because the value of A is the same. So the slit separation is the same, and therefore we have the same position. Sorry for making everybody jump. I might just shock you at some point. I might just do some random shouting just to make sure that everybody watching stays on their toes. By the way, if you haven't already done so, please like the video. I think we've had 15 likes. It's always good to get to a nice round 50. So again, if you don't like the video, I'm just going to keep shouting, and therefore people like Brandon are going to really kind of damage their hearing. Okay, what happens if the viewing screen is moved closer? So we know that lambda equals ax over d. We can therefore say that lambda d equals ax, and provided we have the same light and the same slit separation, d is going to be proportional to x. So effectively, you bring the screen closer, the position of those fringes is going to be small as well. So therefore, d is proportional to x, and that means d goes down. Sorry, x goes down as d goes down. Okay, hopefully that makes sense. Right, and welcome, Joshua just arrived. 17 likes, 20 likes, 21. Come on, let's get up to 50. Okay, now then, this one here, we're going to go back to a question from Wales. Light is a transverse wave. Explain what is meant by a transverse wave. So you know this is just basic GCSE stuff. So we might say that the oscillations are perpendicular to direction of propagation. So you go, lots of nice long sciencey sounding words in there. Oscillations are perpendicular to the direction of propagation of the wave. So the wave is going up and down, or the particles or whatever it might be is vibrating and oscillating up and down, but the energy is being transferred like that. What do we mean by polarized light? So this is more of an A-level question. Polarized light is when you have oscillations in one plane only. Okay, so if we were to look at the light coming head on, if it was non-polarized, sometimes it would be vibrating that way, sometimes this way, sometimes that way, and you'd have all of these planes of oscillation as that light was sort of coming towards you. In actual fact, that does look like the symbol that we use for warning when you have lasers. But if you had polarized light, then it might be something like this. There'd be oscillations maybe just up and down this plane in one plane only. Propagation, G, just means direction of energy transfer. Propagation is the way that something is propagated, the way it's kind of moving, I suppose. Yeah, perpendicular to energy transfer is absolutely fine as well. So now we've got a light source, we've got a polarizing filter. So describe what is seen when a source of polarized light is viewed through a polarizing filter that's rotated through 360 degrees. Now for me, I might just put down a diagram to help. So we might look at the light intensity. Okay, the light intensity is going to go from a maximum to a minimum, to a maximum, to a minimum, to a maximum. Okay, so what we might have here is light intensity, and along the bottom we might have angle in degrees. So we might go from like 0, 180, 360. So that's kind of what's going to happen. It's going to be bright, get darker, get brighter again. After it's gone 180, then it's going to go darker and then brighter. So what you might want to talk about here is it being a gradual change. So it's not on and then off and then on and off. It's going to be gradual. And I suppose it's going to go bright, dark, bright, dark, bright. So you might want to talk about it going bright to dark to bright to dark to bright over 360 degrees. Okay, and again, why not put a small diagram, and then that means whoever's marking your work, they know that you clearly understand the work, that you can see how it goes from bright to dark to bright to dark. Okay, we then have a modern version of Young's double slit. And the reason it's a modern version is because there's a laser. Now, lasers were only really developed in the 1960s, and I think now they cost pretty much nothing. So they're really, really cheap compared to how much they used to cost. Now, originally, when Young did it, he'd have had white light, and he'd have shone white light. And I think sometimes they use sodium lamps. So sodium lamp would give out one wavelength of light, but then they use this sodium light. You remember about kind of spectral lines and stuff like that? Sodium has quite a pure light. They send it through a single slit first of all. That meant the light that came out of this would all be coherent, and then you put your screen over here, and then you know that you've got a coherent wave source. So you've got your two sources there. But laser light is always coherent. So light diffracts at each split. What does that mean at each split? That just means that it spreads out. That's all that diffraction means. Simple. Why is diffraction at the slits essential to produce interference fringes? The reason it has to, so diffraction at the slits is essential because so light from the two slits overlaps. And at this point here, no doubt, at this point, if anybody tries putting in comments and you put the word slit, I think YouTube blocks it. So I often have people asking genuine questions up in the chat. Sometimes there's a few people who just put random stuff and they just get blocked from the channel forever. But sometimes people put legitimate physics questions, but it doesn't let any question with the word slit on YouTube. And no doubt, as I've said that, I'm going to have lots of comments there. Okay, the next question. The fringe separation. Okay, it says here, the fringe separation is 2 millimeters. Calculate a value for the wavelength of light from the laser. So, again, going back to the equation, which comes up all the time, and I'm just going to use it as lambda equals AX over D. Okay, so the separation of the slits, A, or W, I think it is 2.0 times 10 to the minus 3. The slit separation is 0.5 millimeters, so that's going to be equal to 0.5 millimeters times 10 to the minus 3 times 2.0 times 10 to the minus 3. So that's the slit separation times the fringe separation divided by the distance to the screen, which on the last question is 1.5. And again, you should hopefully have seen this beforehand. Who didn't get blocked? Okay, so here that's going to be 0.5 times 10 to the minus 3 times 2 times 10 to the minus 3 divided by 1.5, giving an answer of 6.66666, so that's 6.7 times 10 to the minus 7 meters. But we knew there'd be an answer like this. It tends to be that when you've got questions about lasers, they often use a red laser in the lab, and this is giving us an answer of 6.7 times 10 to the minus 7 meters. So that means you know you've done the right kind of thing, because if we're looking at laser light, it must be in the order of 10 to the minus 7 meters. Okay, the distance from the double slits to the screen has increased to 7.5 meters. State two ways in which the appearance of the fringes of the screen is changed. Okay, so first of all, it's going to be dimmer because the light is going to have to go further, and there's this kind of like, even though it's coming from a laser, it's now kind of spreading out, and we have this kind of 1 over r squared relationship that comes up all the time in physics. Basically, you double the distance, the intensity goes down by a factor of 4. Okay, and also it's going to be more spread out, because we know already that x is proportional to d. So if you double the distance to the screen, then the things get spread out twice as much. So we're going from 1.5 to 7.5, so actually they'll be spread out 5 times wider than they were previously. Okay, then we've got a diffraction grating is used to measure the wavelength. The emerging beams are found, calculate the wavelength of light. So what we've got here is that's 77 degrees. I'm just going to put that as the 0th order, first, second and third. And also we'd have first, second and third down here. So basically we've measured the angle theta of 77 degrees, and that's to the third order, so n is equal to 3. And then we can then say that n lambda equals d sine theta. Lambda equals d sine theta over n. So lambda is going to be equal to d. Well, it's 5 times 10 to the 5 slits per metre. So if there's that many per metre, the distance between each one, d, is going to be equal to 1 over 5 times 10 to the 5. So the separation of the diffraction grating thing is 1 divided by 5 times 10 to the 5, which is 2 times 10 to the minus 6 times sine 77 divided by 3. So times sine 77 divided by 3. I've got an answer now of lambda equals 6.495, so 6.5 times 10 to the minus 7 meters. So even though we've got the same laser, we've got a different value, and it's great to see that Matada and several other people are starting to put the right answers in, which is brilliant. So again, this is roughly the same value, so 6.7, 6.5 times 10 to the minus 7. They're pretty good estimates for measuring the wavelength of light. And again, this is something that you will do in the lab at school, or you should be doing in the lab at school, and you should be familiar with, because there will probably be a question on your exam about looking at the wavelength of light from a laser, either using a diffraction grating or a double slit. Okay, there we go. Next question. Now, Huygens, he did a load of stuff with waves, and basically, what do we mean by a wavefront? Now, there are different ways of representing waves, okay? Sometimes we represent waves like this, sometimes we represent them like this, and sometimes we represent waves like this. Now, all of these are valid, okay? So this is like our side-on view. As we maybe think about putting on things like amplitude. This is maybe the ray diagram to show a ray of light, and this one here is maybe one we often use for things like diffraction and so on. So this one here is basically linking up the kind of the top of the wave. So basically a wavefront is basically lines joining points on a wave that are in phase. So all the bits of this wave here which are at the same phase. Okay, do OCR need to know this? No, I don't think you need to be able to define a wavefront, but it's something that is still worth looking at and actually knowing. So even if you don't have to know it for OCR, it's still really good. What about AQA? I don't think so either. It's something I've never really taught explicitly as a definition, but wavefronts, we use them all the time. So yeah, just learn it. It's basically points on a wave that are in phase are a wavefront. Then we've got something here where you've got some monochromatic light, so one colour, from a laser, blah, blah, blah. One safety precaution that should be taken with this procedure. Okay, don't stare into the laser. To be honest, if you did stare into a laser, you'd have this blinding light and your eyelids would shut, and that would protect your eyes from the worst of it. But laser light, especially in real physics labs, can be really dangerous. So basically, don't stare into the laser. that's kind of obvious. People tend not to do that. The difficulty, though, or the danger, I suppose, in real labs is where you've got a reflective surface, and if the laser light hits that reflective surface, we then get a specular reflection, and that means the laser light all comes bouncing back, and that's when it can do some damage. So it might be that you make sure that when you point it in a safe direction, you do it to maybe a matte background, maybe like a piece of paper, and that means then you don't get this kind of intense reflected light. And then we've got this guy, Thomas Young. He basically did an experiment in 1803, so 207 years ago now. He demonstrated the principle. He couldn't use a laser, obviously. Why didn't they accept the wave theory of light? And basically, this guy, Thomas Young, said, look, light is a wave because we have interference. People were like, yeah, whatever. So basically, why didn't they believe him? Maybe there was no other evidence. Sorry. Yeah, so maybe this is just one thing. No other evidence supporting waves. An answer to the previous one, something said about putting goggles. Goggles on their own will not protect you. So, for example, if I'm wearing glasses, that doesn't stop the light going into my eye. You'd have to be specific that they were optical goggles that were for that wavelength. So sometimes in a lab you might have goggles which are maybe kind of filter out the wavelength of light that laser is, but not just any goggles. Okay, no other evidence supporting waves at the time. So basically everybody said, well, light's a particle, it must be a particle. You know, people like Newton said it's a particle, his kind of corpuscles of light. And therefore, when this guy came along with one piece of evidence, people didn't believe him initially. Okay. Then we've got, again, the same experiment we've seen before. The diagram shows two paths taken by the light after it's passed through slits A and B. The diagram is not to scale, obviously. Point O is a point equidistant from the two slits. Why is there a bright point at point O? So this one here is basically the fact that at point O, some of the light's gone this way and some of it's gone that way, and that means there's going to be path difference equal to 0. And that means then that both waves in phase, and therefore what we have is constructive interference. So basically these two waves will have travelled the same distance. That means there's no path difference. That means they are in phase and they will constructively interfere. Okay, the next bright line is observed at point P. Lines AP and BP show the path of light. So what is the difference in length of path AP and BP? So the difference in path length is going to be equal to 1 wavelength. And it said that the wavelength of light up here was 600 nanometers. So the difference in lengths of paths is going to be 1 wavelength, which is 600 nanometers. And that is the end of the question. Somebody asked about, for the previous question, could they have said that Newton previously thought they were particles? Yeah, I think that would have been a good thing because, Newton, his physics is still established. Newtonian physics is what we still teach you, and it describes the world that we can see around us. And therefore, if Newton said it was a particle and he got so many other things correct, why would people disbelieve him on that? So yeah, the fact that basically the scientific convention at the time was that light was a particle, and one experiment showing its waves doesn't prove it's a wave. Obviously, now we know that light isn't a particle and light isn't a wave, but it is also a particle and a wave at the same time. And the kind of models and the way we think about things are just models to help us understand the world around us. So that is the end of the lesson on waves. Basically, what we've been doing is, for the last sort of week or so, we've just been doing waves, so about interference, standing waves, diffraction, and so on. Later this week, so tomorrow and Wednesday, we're going to be looking at some materials. So this is very much the engineering kind of bits of physics. I know that lots of you probably watching this at the moment are thinking about going to do engineering at university, perhaps at some point in the future. And if you're thinking about doing mechanical engineering, then the videos or the live stream and the lesson for tomorrow and Wednesday are going to be really useful. So yeah, we've got questions about the spring constant, we've got questions about stress, strain, Young modulus, and so on. And yeah, basically that's what I'm going to be going through tomorrow at 2 o'clock. So I hope all of you can join me there. Hopefully all of you are well at the moment, and until schools starting, whenever that may be, just keep doing physics. And the more physics you do, the better you will get, and the more attractive you'll look. You'll get a better partner in life, you'll get a massive house and a fantastic job, and just have to work 5 hours a day because you are physics masters. So until next time, I'll see you tomorrow. Thank you very much. Studying A-level physics, I've made hundreds of videos covering the most important aspects of your course. At alevelphysicsonline.com, you'll find them all organised by exam board and then by topic. For a small one-off payment, you get instant access to all the Year 13 content. And at $19.99, it's far cheaper than you might expect. That's less than a meal for two at Nando's. Gain access to all the videos to learn the physics that you require for your exam. Put simply, for less than £20, you'll get full on-demand access to all the videos that you'll need for A-level physics. Studying A-level physics, I've made hundreds of videos covering the most important aspects